Okay, I have recorded the class. Today we are going to learn non-parametric regressions. 3 non-parametric regressions I'm going to discuss. This is known as the kernel regression. Number 2, local polynomial regression. And number 3, spline regression. Spline regression. Okay, this is 1964. This is 1977. This is 1995 or 96, something like that. Okay, very new. So statistics is relatively very new area. Okay, before that it was with the mathematics department. 1905 statistics department was opened in Royal Society in England. So after that US opened statistics department in late 90s, 1930s, 1935, 1929, something like this. Okay, so this, as you have seen the years, these are less than 100 years ago. Okay, even like less than 60 years ago, these are. What does this mean? Non-parametric regressions. There is no parameter. Understand? Non-parametric, there is no parameter. What is the parameter? If this is the regressions that you have learned, in this case, beta 0 is a parameter, beta 1 is a parameter. Okay? Beta 0 is the intercept, beta 1 is the slope. Beta 1 determines the linearity. Linearity comes from beta 1. Okay? But non-parametric regression is what? Non-parametric regression is this one. Y equal to fx plus epsilon. Understand? Y equal to fx plus epsilon. So you do not know the form of the fx. You do not know. You do not know. Do not know. Okay, you do not know the form or structure. Form or structure of the regression line. Regression line. Okay. And when these models are used, we also call functional data. So for the functional data, these 3 non-parametric regression are used. Okay, now let me explain what is functional data. Okay, functional data. Let me tell you, this is linear equation, right? This is linear equation. Here is x, here is y. Okay, but functional data tells is what? Here is x and here is fx. Okay, this could be like this. Okay, are you understanding? This is called the fx will take form. Okay, it could be like this. It could be like this. Okay, it could be like this. Okay, so I put here something. It should not come like that way. It should like this way. So functional data means, so see how the scientists, they identify this procedure. So suppose you have data x and fx. Suppose x equal to what? Time, and y equal to what? Speed. Okay, and this is the time and speed, or distance or speed, something like that. So I want to put here time. I want to put here time. Okay, and then I want to put here distance, something like that. Okay, so how can, for different time, different distances are crossed. So first 1 hour they crossed maybe 70 miles. Second 1 hour they crossed maybe 73 miles. Third 1 hour they cross maybe 50 miles. Fourth one they cross 20 miles. Understand? So in that way, it is like 70 is in here, 60 is in here, 50 is in here. So first hour, second hour, third hour, fourth hour, fifth hour, data is going like this, something like this, right? So the question is how to construct this curve. Are you understanding? Now you can say that, hey, professor, this is very easy. How? This is very easy. Why you're teaching us these things? Then you said that how it is easy? Immediately you answer, at first hour, we go 70 miles per hour. So this is, as the second hour, we go, suppose this is 70, we go suppose 80 miles per hour. And third hour, we can go in here. Fourth hour, due to the rush hour, we come in. Fifth hour, we go like this, that. Understand? This is what may be your question. And the seventh hour, we will again guide you. So this is very easy. This is very easy. We connect distance. This could be your answer, right? Yes.
Time distance should increase.
Okay. So this distance should decrease. But first 1 hour, how many miles I go? 70 hours, 70 miles. Second, this is what the miles is. Here is time. Here is miles or distance. First 1 hour, I go 70 miles. Second 1 hour, I go 85 miles. Third, I come down to again 70 miles. Okay. Per hour, how much distance I cover? This is what I want to plot. Understand? Do you understand? You can answer this. This is easy. Are you understanding? If you say this is easy, this is just a plot, scatter plot, and adding the line. This is not the prediction. This is not the prediction. Here is lot of values, right? 71, 72, 73, 74, right? This is not the prediction. Are you understanding? This is just adding the line, right? This is not the predictions here. This is not the prediction. This is just you added from here to there. You added from here to there by line. Understand? This is called the line plot. But we want to develop a mathematical regression model that will construct this curve like this way. And then we can say now at 1.5, we cross that many miles. Now that will be true. If we can mathematically develop some regressions, and then we can say that this is a prediction. Are you understanding? Currently, what I have in here is just corresponding to each time point. I am plotting the miles that was achieved by my vehicle, and you are connecting these things. But between these 2 points, this is just the connection line. This is not a prediction. Are you understanding? So if we construct a curve by using mathematical model that is known as the smooth curve, then we can predict it. We can say that at any line we can predict it. Understand? So before going to the mathematical thing, let me show you something. Okay, let me show you something. CAR, cars, okay? Cars is the data. Are you seeing speed and distance, right? Two variables I have taken. Okay. I want to construct a smooth curve. In order to do that, you have to order the data according to this format. According to this format, if this is my speed, this is my distance, I want to predict. Okay. So now take a look at that. This is the code I have provided to you. Let me explain these things. Are you seeing local polynomial smoothing bootstrap code? Okay. So what you need to do in this homework, first of all, in the homework questions, I have asked you to use Python. If you cannot use Python, cannot get the code from the Python by using online resources, then you are allowed to use R. But previous year, I saw like 90% students did the homework by using Python. Understand? Now, let me explain these things. This is the all code that I have written in here. This is the all code that I have written. This is for the local polynomial one. Okay. I have computed all of these things in here. This is done. So what I did, I just run the local polynomial code. Okay. Run it. The code is run. Understand? So I have run these things. Now I want to come down to the part in here. So this is testing smoothing curve. I run the first one and then running the testing smoothing on testing smoother on the curve. Now take a look. I am running now this part. Are you seeing the curve? Understand? So as speed going up and distance is also going up. So this is what the meaning is. What does this mean? In this line, I put speed, and in this, I put distance. And these dots are what? So suppose corresponding to this is when speed is 10, and then distance is like that. When speed is 10, distance covers something like this. When speed is 10, distance covers that. By using this dot, we constructed this smooth black line, which is the non-parametric regression line, smooth line. Okay? Are you understanding? You understand, right? You understand, right? So now take a look at that. I write local polynomial and then come run this one. Again, I will come again that one, which is the kernel. But before running the kernel one, I have to run the kernel code. Let me take you to the kernel code. This is the kernel one. I just run the kernel one. Okay. After running the kernel one, now I want to run this one. This is the kernel. Three regressions, three non-parametric regressions. Okay. Three different chunk of regression, non-parametric regressions, and their output. All the output is given at the end. Now, if I run this, are you seeing it is different from that one, right? It's changed, right? So this is called the kernel one. And then I want to do the spline one, which is the last one, which is the last one, which is the last one. And then I run this last one. Seeing that, right? So I have provided code to you and give the explanation. So down the road, if someone say you something non-parametric regression or functional data analysis, which is nothing but local polynomial regression, kernel regression, and spline regressions. All of these three regressions are developed in last 60 years. 1964 kernel, 1977 local polynomial, 1996 is spline regression. Clear, right? So in your final exam, lot of questions will come from there. Please try to understand entire lecture attentively, and what I am telling you, try to memorize these things. Okay. Now, if I want to run these things, entire things together, I will get all these three curves together. Are you seeing all of these three together? I got like this way. Or I can change it to 1/3. If I change it to 1/3, then see how the graph looks like. Okay. So I want you to do the homeworks. R code has been provided. Just search the internet. You will find the Python code, and the Python code you can do the homework. I will be happy. But if you cannot find the Python code, R code is fine. So again, this is called the smoothing regression curve obtained by local polynomial. This is the dot. Dot represent the value of the distance corresponding to the value of the speed. Corresponding to the value of speed and distance, we got a dot. Dot is the raw data, scatter plot. One in X, another one in Y. So if you put these things, the dot means that. And solid black line, smooth line is the non-parametric regression curve or smooth curve. Okay. And red dotted line is the 95% bootstrap, pointwise bootstrap confidence band. Clear, right? So I have mentioned everything now. If you want to go there, here is the homework. Download the homework. This homework, homework 5 on non-parametric regressions for DS 480 G predictive analytics, due on that. I encourage you to do the homework by Python. If you cannot, then use my code.
Sir, what about homework 4?
Homework 4.
When is it due?
It is due today, right? Yeah. It is due today. Okay. So now, homework 4 is on linear mixed effect model and quantum regression. Okay. Linear mixed effect and quantum regression. Did you watch the video?
Yeah.
Okay. So when can you use quantum regression and when you have to use linear mixed effect model? It will be the questions for your like conceptual final exam. It will be the question. Try to watch my videos. Okay. Life is very easy now. All the videos, YouTube channels I have opened and upload everything in there, right? Did you subscribe my channel? Yes. Subscribe it, watch it, all of these things. And not only that, there is all mathematical derivations of that. And the mathematical derivations that I discuss in there, it will be invaluable properties, invaluable things in your life, because certainly sometime someone will ask you, well, I know the applications, but how this come into an existence? You understand why I emphasize these things? You are graduate students, you need to know how something come into an existence. If you know that things, then you can further advance that things. You can advance that things to the next level, right? So that is why foundation is very important. Okay, so for this homework, you must use C1 BDHS and C2 CPD data. These two data is already in the Western Online. Okay, already in the Western Online. Could you please shut down your computer? Tell me what you should listen, because I want you, all of you, to succeed in your final conceptual exam. Okay? Then if you do not do well, I cannot give you any favor. Okay, these two data, C1 BDHS and C2 CPD data, are available in the Western online. So if you have a student ID which is odd, use the C1 BDHS data. If you have a student ID even, then use C2 CPD data. Okay? Now, please follow the steps below to fit three non-parametric regression model known as local polynomial regression, kernel regression, spline regressions. Okay. Subset the data by taking two variables such as age and another variable. Both of the data must have a age variable. Okay. Both of the respondent age, something like that, is in there. And any variable you can take, maybe systolic blood pressure, diastolic blood pressure, or height or weight, respondent height, respondent weight, marriage to first birth interval, all of these things. So denote age as a X and denote other one as a FX. Denote this new data as a D2, which will have only two variables such as age and another variable of your choice. We want to fit this model. Okay. Where fx is the unknown regression function and E is normally distributed with mean 0 and variance this. So step 2, take a random sample of size 100 rows. From the entire big data, you will take a random sample of 100 rows. Okay. If you fit it for the entire data, then it will be very messy. Okay. Very messy. So read the question. Okay. And you already know that I grade you things very carefully, right? My research life is almost close to 0.5% or like 5% or 10% because of teaching and grading all of these things. It is taking a lot of time for me. I have a question. Okay. All are you? What questions you have?
Okay, so I was asking,
I cannot hear you.
I can hear you.
Tell me now.
Okay. For this non-parametric regression, so are you saying that we only use them when we don't know the function of the model?
Exactly. Exactly.
Okay.
That could be one question. When we use non-parametric regression, if you do not know the functional form, so if you do not know, like linear regressions, you know linear rank, right? Quadratic regressions, there is some quadratic. If you know like this way coming, you can use that thing. Okay. But the functional data or non-parametric regression will be used when you do not know, or scatter plot does not provide you any support whatever. Or scatter plots, if you plot the scatter plot, it is showing you zigzag pattern. Okay. It's showing you going up, down, and then up and down, something like that. So functional data is that. Thank you for asking it. So and then rest of the thing feeds local polynomial smoothing estimations with 95% bootstrap confidence band around the smoothing curve, where age will be independent variable and other variable of your choice will be dependent variable. Fit the kernel smoothing estimates with 95% bootstrap confidence band around the smoothing curve, where age will be independent variable and other variable of your own choice will be dependent variable. Fit the spline smoothing estimates with 95% bootstrap confidence band around the smoothing curve, where age will be independent variable and other variable of your own choice will be dependent variable. Plot these three smoothing curve with 95% bootstrap confidence band in a 3x1 grid that I already showed you, right? Code has been given. First run our code between beginning of section 1 to the end of section 3. So section 1 and section 3 means what? Let me take you there. So where is my R? Here is my R. This is section 1. This is section 1. Section 1. And then that will be my section 2. Section 2. And then this will be my section 3. Section 3. Okay. And then after running these things, if you run these three things together, it will give you the results. So let me save it and upload it so that those students who came late, who pass this so that they can sign. Okay. So I save it now. Let me go there in the Western Online, and I just want to delete these things. Permanently delete these things. Now I want to upload this again. It should be in the download folder. Okay. Okay, now I want to start with the kernel regression first. Kernel. Remember, when I do these mathematical derivations, write down all of these things and try to understand what important word I am telling. So in your conceptual exam, you have to write 1 or 2 sentences for each of the topic, okay? Okay. Let me start with this kernel regression. Yeah. So kernel regression first of all, I have to define the definition of kernel. Definition of kernel. Do you know what kernel means in non-mathematics or non-science sense? Do you know the coconut? Inside the coconut, what we get? Sometimes when the water dried up, something like very delicious, right? That is, the English word is kernel. Understand? Why I said this? Do you understand that coconut, when the water dried up, then inside that things, that delicious thing is called the kernel in English. The kernel is a very important thing. That means basic thing inside the things. So that is, the reason is that kernel has some properties. Okay? This is what statistician define. I'm going to give you the explanation why I bring the example of coconut. Okay? So let x1, x2, xn be IID sample. What do you mean by IID? Identical. Who said identical? Identical, right? What does this mean? Can you give me explanation?
The variance is the same.
What? The variance?
Is the same everywhere.
Yeah. So identical means what? Suppose you have a binomial distribution, which is this. X equal to X and Cx p to the power X q to the power n minus X. Okay? So your probability of success is P1 and probability of failure is Q1. I have a binomial distributions X equal to X and Cx P2 to the power X Q2 to the power n minus X. Understand? My success probability is different from your success probability. So these are not identical. Understand? On the other hand, in the classroom now, there are 7 students and 3 online students, 10 students, and myself, it is 11. Each and everyone has these distribution and Cx p to the power X q to the power n minus X. That means P and Q are same for all. You have same P 50%, this P probability of success, this P probability of failure. You have 50% of success, you have a 50% of failure, I have a 50% of success, I have a 50% of failure. Then this is called the IID, independently and identically. And see, each person is independent, right? Your thought process, your sleeping behavior, your interaction behavior, your all the behavior is different from another person's, right? So that is called the independently and identically distributed. So X1, X2, Xn are IID sample drawn, IID sample drawn from some univariate distribution, univariate distributions with an unknown density function, at any point X. Okay, at any point X. So this is the IID random sample drawn from some univariate distributions that is unknown density function. That means this is a density function which has a mathematical format like this, which is known as the exponential, x greater equal to 0 and lambda greater equal to 0. Okay, this is called the exponential density function, exponential density function. This is the exponential density function, remember. So this is a known, right? But here I do not know. I do not know the f. How f look like, I do not know. Are you understanding? Are you understanding? I took a sample. Suppose I took the sample of your height from you. How many of us? 12 of us. I get height. But I do not know height follow normal distributions, or height follow exponential distribution, or height follow negative binomial, any distributions. That we do not know. Are you understanding? Are you understanding? So I take like how much money you make each week. I took that sample. I take sample. He said that I make $400 each week. She said I make $500. I said I make $2,000. Understand? So those 12 observations is in there. But I do not know whether these observations is coming from the income distribution known as the parity distributions. I do not know. Clear, right? Because non-parametric regression means what? Non-parametric regression means you do not know the function form. So that is why I said in here unknown density function. That unknown density function we need to estimate. We need to construct. So that is why unknown density function. We are interested in estimating the shape of this function. This function means this unknown function. This unknown function. Okay? This unknown function we are interested to estimate. Estimating the shape of this function f. This is the unknown density function f. Unknown density function f. Okay? Unknown density function f. Now, kernel density estimate of f, kernel density estimates of f is given by, this is what is unknown. How can we estimate this? And there is a kernel density estimate of f defined by this f, and this is a x h equal to 1 over n sum of n, then I goes on to n, k h x minus xi could be written as 1 over n sum of n, I goes 1 to n, then k x minus xi divided by h, and then finally divided by h. This is what the definition or given by the mathematician and statistician. If this f is unknown, this f can be estimated by this kernel density estimator. I don't know whether you are understanding or not. Let me again explain these things to you slowly and very clearly. Okay? Slowly and very clearly. You and we all 12 or 15 people possess many different characteristics, right? Okay. Suppose one characteristic that I want to take from you, how many minutes you walk each day. Okay. So he said I walk 20 minutes. He said I walk 60 minutes. You said you walk 40 minutes. I walk 10 minutes. Another girl says, I always stay at home. I'm a homemaker. I don't work. Okay. So these are the how many minutes you work each day informations you are given. So I have all individual informations, but I do not know from what distributions the number of minutes that you work are coming from. That I do not know. And I do the some plotting. Number of person is in here. 12 persons I put in the x-axis, and their number of minutes I put in the y-axis. Let me write it more clearly so that you can understand these. You can understand these equation. These equation you can understand. How did I write it? So I put here number of persons is in here. Number of persons. Okay. 1, 2, 3, 4 up to 12 persons is in there. 1, 2, 3, 7. And then there is a minutes. Okay. So there is all the minutes coming in here. So I got in here. So I found that well like this way. And I know this does not follow any probability distributions. Any parametric distribution, this does not follow. Clear, right? So the unknown thing that I explained, unknown density functions, so that is why I am giving example after example. If this is the scenario, the mathematician, the statistician, they said that these unknown things can be estimated. This is the unknown, these things could be estimated by this. Okay, n equal to number of observations. H is the bandwidth. Bandwidth known as the smoothing parameter. Smoothing parameter. Okay. H is known as the bandwidth and smoothing parameter. K xi, x minus xi divided by h is a a weighting function, kernel and weighting function. Kernel and weighting function. Okay. So statistician and mathematician said any unknown density function f can be estimated by using this formula, where h is the bandwidth known as the smoothing parameter, which I'm going to discuss. And then the k that you are saying, it has kernel. This is the kernel and weighting function. This is known, kernel, known as the weighting function. Kernel is known as the weighting function. Now I want to explain you what is bandwidth h. What is h? Okay. Now try to understand. Try to understand in here. Here is your x, here is your fx. Here is your number of people, here is the number of minutes you work. You got like this way. Understand? So are you, and then there are other data. Are you smoothing it like this way? Like this, that, this, or that, something like that? Or you are smoothing it like this way? So bandwidth means windows. How small or big your smoothing windows is. If smoothing window is very big, then you can, if smoothing window is very big, let me put the red color. Smoothing window is very big, then you can put like this way. This is your curve. On the other hand, if smoothing window is very small, then your curve looks like this, very wiggly. Understand? So bandwidth is a smoothing parameter which you have to select by cross validations. Let me write it. Bandwidth is a smoothing parameter which is selected via cross validation. That means for which bandwidth value the cross validation score or mean square error is minimum, that would be selected. So h would be a number. It could be 1.5, it could be 2.5, it could be 0.5, it could be 7, something like that. But that value must be selected by using cross validations. Cross validation score is computed for each value for the bandwidth. We compute mean square error. From the mean square error, for the value of the bandwidth, when the mean square error is minimum, we will select that bandwidth value as the smoothing parameter value. Understand, right? So see, I have written a lot of things in here. You could expect the questions in here about what is bandwidth. Okay, right? So bandwidth means, suppose you have a data is in here, in this format, these are your data. Are you doing it over smoothing like this, or you are doing under smoothing like this? If bandwidth value is very high, there will be over smooth. If bandwidth value is low, then there will be spiky smoothness. Understand, right? Okay. If bandwidth value is very high, there will be a over smoothing problem. If bandwidth value is very low, then there will be under smoothing problem. That means spiky or over smooth. If bandwidth value is very low, the smoothing estimate will be spiky. If bandwidth value is very high, smoothing line or smoothing estimate will be over smooth. Clear, right? Okay. So now, after writing these things,
How will you calculate H?
what?
How will you calculate H?
H will become calculated. That is what I said. Bandwidth is a smoothing parameter which is selected by via cross validation. Cross validation means what? You take a H1, you take a value of bandwidth H1. I took H2. Another person take H3. Another person take H4. For each of these bandwidth value, we compute cross validation score, which is minima, which is the like mean square error sometimes said. For what value of this bandwidth mean square error is minimum will be considered as the bandwidth value. So you took one, she took one, another person take one, then everyone is fighting. My one is true, my one is true, my one is true. So then which one I should consider as a gold standard? Bandwidth value for which cross validation score is minimum will be accepted. Understand? Value of the H or bandwidth for which cross validation score is minimum will be considered as a bandwidth. Okay, so after these discussions, now let me define. We had these things: F prime H X. These things equal to, I have to use this one. What I had 1 over n sum of k x minus xi divided by h and then here is another h. So we can write here 1 over n h sum of n I goes on to n k x minus xi divided by h. Okay. Clear?
The value of K.
What is the value of
K.
K? This entire thing is just one thing. This is known as the kernel. K x minus h divided by h. Okay, this is called the kernel. This entire thing is a kernel. Now, what is kernel? Okay, there are many kernels, but kernel has two must properties. First property is kernel satisfied. This is integrate to minus infinity to plus infinity. Suppose ui equal to xi minus x divided by h. Okay, so I write here in other way. So it could be written as x minus xi, something like that. So it is just the abuse of notation. So in that way, kernel has two properties. Every kernel must have two properties. What is that? K of u and then d of u equal to 1. Number 2, this will be symmetric kernel for all u. So symmetric kernel means what? Suppose this is 0, this is negative infinity, so this is positive infinity. Okay, or it could be like this 0, this is negative 1 to positive 1. Understand? This is symmetric. Any function, if you can write that satisfy these two property, is called the kernel. You cannot take any function. You have to take a function that must satisfy these two characteristics. Are you understanding? So if I write what characteristics a kernel must satisfy, you have to write these two conditions. Otherwise, it will not be a kernel. Understand? Take a look at that. By giving definitions of the property of a kernel, a unknown density function which we do not know, this unknown density function is estimated by using this formula. Isn't it a fun in 1964? Product kernel. Understand? So there is a kernel density estimation and histogram approach, a lot of things, but I am giving you just the basic idea. So some of the kernel, if you ask me to name or write, this is just the background I have given you. Uniform kernel, which take k of u equal to half. Okay, k of u equal to half under the condition absolute u less equal to 1. Okay, number 2 is called triangular kernel. Triangular kernel. It looks like this. 1 minus u, then u less equal to 1. And then number 3, Ipa-Nichnikov kernel. Ipa-Nichnikov kernel. This kernel satisfied all like optimal properties. So that is why this is called the optimal kernel. 1 minus u square and u less equal to that. And finally, you know this one, Gaussian kernel. Which is known as the k of u 1 over twice pi this is what. Okay. Now let me convince you by proving these things, these two things. Okay. By proving these two things, I can convince you. So let me show this one. This one is what? U takes value positive 1 to negative 1, right? This means what? This means equal to that, right? Right? Do you understand the difference between this one? X, absolute X greater equal to 2 and absolute X less than 2. What is the difference between these two? If you take out absolute sign from there, then this will become X less than 2 as the X less than minus 2. If you take out absolute sign. If you take out absolute sign from there, then what you are getting? X less equal to minus 2 and X greater equal to plus 2. This is the meaning of these two things. You understand this, right? Okay. So now let me show the two properties that I discussed. This equal to that. Now, first one, right? First one equal to minus 1 to plus 1. This is the property I want to prove. And then we have k u d u, which I can write 1, 1, and then there is a half du. Now I want to say here half u, and then 1 minus 1, then half u plus 1, equal to half times 2 equal to 1. This is a simple integration. You know this integration, right? You know the integration and differentiation, right? So this is the proof. I have proved this one. Okay. Second conditions in this case, whatever value you will plug, as this is true, if I put here negative or positive, it is always half. So second condition is also proved. I'm not going to prove rest of the thing. It is just the simple mathematics involving integrations. So far, last 1 hour, I have discussed about the kernels and how a unknown density function, from where I take the sample, I can estimate. Understand? Samples are coming from a probability density function, which I do not know. Whether it's going like this way or it's going like this, many different format, thousands of different format it can take place. Based on the value of the age, if each of us take a subjective age, that means we are not interested in any mathematical procedure to determine bandwidth, we will choose subjectively. You choose 2 bandwidth, he choose 1.5, I choose 3, he choose 7, you choose 0.1. Your one will be very spiky, he choose 2, 10, very high, his one will be very smooth, over smooth. So I have built up now the foundation and an explanation. What is bandwidth? Bandwidth is a smoothing parameter. What is kernel? Kernel is a weighting function. A kernel satisfies 2 properties. Number 1 is integrate to 1. Number 2, it is symmetric. Okay. By using these, the statistician developed kernel regression and local polynomial regressions, now which I am going to develop. Okay. Let me see what else we have. Bandwidth of a kernel is a free parameter which exhibits a strong influence on the resulting estimates. Okay. Now let me write these things. So how this gentleman asked me question how the bandwidth are selected. So let me write these things. Bandwidth. The bandwidth of a kernel of the kernel is a free parameter, which exhibits a strong influence on the resulting estimate. Now MISE, mean integrated square error, for age we have to compute this f hat hx minus fx square dx. So I took H1, you took H2, another person take H3, another person take H4, another person takes H5, H6. For all of this, we will get this value. For what value of H, this value is the minimum, will be considered as a bandwidth value. Clear, right? Okay. Okay, let me now start deriving kernel regression. Question? Let me derive now kernel regression. Suppose that we have a random sample. Now the derivation starts. Random sample of bivariate data that x1 fx1 x2 fx2 xn fxn. These are the data we have up until xj fxj. These are the bivariate data coming from a joint PDF. Joint PDF known as the z x comma fx. Okay. For example, x equal to number of person, fx equal to number of minutes the persons worked. So this is the data is coming from this joint PDF. Okay. Now, according to the, as I mentioned, mx be an unknown regression function. Let mx be a unknown regression function. Then the non-parametric NP, non-parametric regression model. NP means non-parametric regression model is f of xj equal to m xj plus epsilon j. J take value 1 to up to j. So epsilon j has a mean 0 and variance sigma square. This is the epsilon j error. The same assumption as linear model. Okay. Now, if I want to take the expectation on that, I want to take expectations on that. Okay. If I want to estimate these things, which is, so we usually parametric regression, we like this, right? Beta 0 plus beta 1 xi plus epsilon I. This is what we usually write, right? So similarly, I write it in here. We estimate these things. Now we estimate here that thing. Clear? Are you getting it? In the parametric regression, we estimate these things. Now we are going to estimate that one. That is the unknown quantity. And this is f of xj, which will be the data it is given. X and fxj will be the data it is given. But now we have to formulate it. How can I formulate it? Fx could be computed by doing these things. Fx given x equal to x. And then by integration formula, this will be fx g of fx given x d of fx. Okay. Now, as this is a conditional, that could be written further by using this. This could be written further by using this fx and then g of x fx d of fx over g. I have to go there again. Theta fx. Okay. Now, if you have a confusions, how can I come from here to there? The answer is probability of A given B could be written as probability of A and B divided by probability of B. This is one. And another one is this. If you x comma y and then dx, if you integrate this, then you will get f of y. I use these two things in here to get this. Okay. Rest of the thing very easy. Take a look at that. This is the unknown, right? As I mentioned in here, draw in the linear regression. In the linear regressions, the similarity, I am drawing similarity between this and that part. Okay. So this part equal to this part in the this non-parametric regression part exactly equal to the parametric regression part of the linear regressions. Okay. So in the parametric regression, we estimate these things. In the non-parametric regression, we have to estimate these things. This could be estimated by expected average of f of x given x. So now this conditional expectation can be written like this way, and this conditional probability can be written like that way. So now we have a very beautiful function. Now we have a very beautiful function. Let me write it very beautifully. Fx g x comma f of x d f of x divided by g x f of x and d f of x. Clear, right? So these reduce to that, right? These come into that, right? How mathematics come into that? Okay. Now these are unknown, right? I said these are unknown. These are unknown, right? As these are unknown, didn't I tell you statisticians and mathematicians, they gave a formula to estimate these things in here? Didn't I tell you? If this is unknown, this is estimated by this, right? If this is unknown, this is estimated by that, right? This is what I said at the very beginning of the class. Now we have two parts. One part is in here known as the numerator. Another part in here denominator. We want to estimate these things by using kernel density estimator. We want to use this in here that I mentioned in there. Okay? And when I showed you the code and run the code, they have actually estimated these things. All of these things they have put there. Okay? Now, take a look at that. This one is known as the g hat x comma f of x. This is what now I am estimating. Could be estimated by using j, h, x and h, f. Because there are, one is x, for that bandwidth is this hx, and fx, that one we have a bandwidth of h of f. And then sum of, this is called the product kernel. This is a joint, so that is a two product kernel, two. That was a univariate. That was just fx, so that is why only one kernel. But this is now joint. This is now x and fx, so there will be a two. One is for the x minus xi divided by hx. Another one is for the fx, which will be definitely k. Here is the fx minus fxi divided by HF. That's all. And now you can say that, well, what is this? This is what you can choose one of the kernel that I mentioned before. Uniform kernel, triangular kernel, Ipanichnikov kernel, Gaussian kernel. That is a specific value. You just plug in there those functions in there and then multiply the plugging the value of x and fx, you will get your kernel value. Are you understanding? So when I first read these things, I said that, wow, how can this possible? Something is unknown, and then these people, they are estimating these things by using that. Didn't I say to you x and fx are coming from an unknown distributions? I have x and y, but how the function behave now, I am figuring out that one. It is not even properly 60 years old, okay? 1964. Okay, so this is what one part is gone. H is the bandwidth, everything else I already mentioned in there. Now if you plug, if you insert all of this in there, then we get in J, I goes 1 to J, and then here is a 1 over J, and then this will be just K H X C. The formula has been little changed as I mentioned earlier, J, and then here K F of H of F, and then here F of X minus F of XJ. Sorry, I mess up with the I and J, it should be J. So this is what one part is done. So that means this estimation is done. This estimation is done in here. Okay, as this estimation is done, now I just want to add one thing in here. My numerator is this. My numerator is this. My numerator was F and G hat X, F of X. This was my numerator. So in this numerator, I can put what I got from the previous steps. I plug here F and then plug here J. Small j goes to J. K H X, X minus XJ. And then I put here K HF. Then I put here F of X minus F of XJ. And then I put here DF. Okay. Now take a look at this one. 1 over J. And then this is now remaining J K X minus XJ F of X J, this part. What these integrations and that part will become one. This integration and that part, because this integration is taken over the F and DF, so that will be one, and this part is remaining in here. This part is remaining in here. Because kernel has a unique property, it's sum to 1. Okay? So this mathematical derivation are not going to be asked in your conceptual exam, but you will be asked what are the two properties of a kernel. Okay? What does kernel do? Kernel is a weighting function. Okay? So this one part is gone now. Now for the denominator, you have a question. So let me again explain these things. Just take a look at this. This is a parametric regression, which we know. This is a non-parametric regression we do not know, right? This is what we estimate. Beta 0 and beta 1 we estimate. Beta 0 and beta 1 we estimate. Then we feed the regression line. Here we need to estimate mx. So mx equal to what? It is again average regression. So as it is average regression, mx, and this is the function, I have to take a expectation with respect to that. If we take with respect to that, then that is what this expectations and all of this come into this. And finally, the way the statistician and mathematician said that if your densities are known, you do not know from what density your data is coming, then you can estimate it by using kernel density estimator. Kernel is a weighting function. Within kernel, you have a bandwidth or smoothing parameter. And then they proposed it, and then they show some practical example, and the paper was accepted. And this system has a wide range of application in non-parametric regressions. Many places. Okay. So some people, they take the shower, they are thinking. They eat something, they are thinking. They go to the bathroom, they are thinking. That's the way these things come into an existence. You understand, right? When I was first reading this thing and trying to understand this, wow. They do not know how the function behave, but now they mathematically compute these things. Okay. Before that, before 1964, what people do, they do the scatter plot and then they join the line. They say that this is the line, but that is a line graph. That is not an estimator. But when you get the entire smoothing curve, each point is giving you the estimate. Each point is giving you the predictions. Understand? So I'm repeating these things multiple times so that you can understand. Okay. So now let me go to the denominator. For denominator, we have this g of hat x and f of x and then df. Okay. 1 over j. J goes 1 to this khx x minus xj khf fx minus f of xj d of f. This is what the denominator part of that. From there, we can see this sum j k hx x minus xj, because this is the kernel part which is equal to 1. Okay. So this is the estimate of fx. Okay. This is the estimate of fx. Now, this is the denominator, and previously we got the numerator. From there, if you plug the numerator and denominator, what you are getting? mx numerator and denominator. Okay. In the denominator, you will get 1 over j sum of k h x x minus xj. Okay. And in the numerator, you are getting these things. In the numerator, you are getting 1 over j sum of k h x x minus xj f of xj. J goes like this. Okay. Now, if I want to consider this thing, this is if I consider these things as a one entity, this and that are cancelled. If I consider these things as a one entity, which is equal to, suppose, I can write here W H X Xi minus Xj. If I write like this way, then this will be reduced to some W hx x minus xj f prime of xj. So j equal to 1. And this is called as the weight. This is the functional estimates. Okay, that this is what the like the density estimates univariate exercise, and it is multiplied by this weight. So what they are doing in here, they are multiplying this with that weight. They are constructing a curve like this way. They are constructing a curve like this way. They are constructing like curve like this. So any functional data, now you can construct a smooth curve, and each of these point is the prediction. Okay, but if you just do the line plot by adding like that way, then it will be called the line plot. And the line plot, you can only say the trend. From first point to second point, the trend is going down. Second point to third point, trend is going up. Third point to fourth point, trend is similar. Fourth point to fifth point, trend is going up. That is what you can say. That is called the line plot. But this one is not a line plot. This is what called the smoothing curve. Smoothing curve or estimated non-parametric regression curve from the functional data. From there, you can make predictions. Okay. Yeah. So now you can take maybe 10 to 15 minutes break, and then I will, after that, I will cover local polynomial regression and spline regressions. Okay. So we will start at 7:40. We will start. Okay. Did you sign? Okay, I have started resuming. I have resumed the recording. So let me start with now second non-parametric regression method, which is known as the local polynomial regressions. Okay. Are you ready?
Yes, sir.
Local polynomial regression, polynomial. Our purpose is what? Our purpose is to estimate this fx, right? Our purpose is to estimate this fx. Okay. So now take a look. This fx could be written by Taylor expansion. By Taylor expansion, these things could be written f of a plus prime of a factorial 1 f double prime of a factorial 2. There is a x minus a, and there is a x minus a square plus x minus a cube which could be written as sum of infinity n goes 0 f n a divided by factorial n x minus a to the power n. This mathematician said that any function I can express like this way, and then I can compute this. So we are going to use this Taylor expansion to expand our non-parametric function, and then we will express that finally in the format of a regression equation or regression model. So suppose that in this, so what is this? Can any one of you tell me? F double prime of A, what does this? Double differentiation, right? So that means differentiability is a condition. Suppose that fx is p plus 1 times continuously differentiable with respect to x belongs to x. So the condition is that they are assuming this is p plus 1 time continuously differentiable with respect to x, and then fqx, which is the differentiation, be the qth derivative of fx. 1 less equal to q less equal to p, and beta qx could be written as fx over factorial q. Now, if fx by using Taylor expansion, fx could be written as beta q a0 x minus a0 q for x in some neighborhood of a0. For x in some neighborhood of a0. So now this has been expanded, and this is just like that. Okay. Now remember, y has been written as beta 0 plus beta 1 x plus epsilon I, right? We just bring this one from right side to left side in order to write it in this format. F of xj, this is f of xj, I am summing over j, and then now subtracting beta k x my x minus x to the power q. I have taken these things. Q get value 0 to p. And then I'm just squaring this. Okay. Now I have to spend some time in there. We have we have these things. We have these things. We just brought here this right hand side to in here. And then after bringing it in here, we just take the square and sum it up. This is kind of error sum of square. So in this case, this is error sum of square yi beta 0 minus beta 1 x I. This is equal to error. Then we take the square and then we take the sum. Exactly same thing we have done in here. Function x has been expanded. See, when it will take like 13 years, they said that, well, kernel density they have used there. How about on the fx, we just want to expand it by the Taylor expansion. They use Taylor expansion and subtracted one side from the other side and then take the square and sum. This is just the error sum of square. Okay? This is just the error sum of square. Now, this error sum of square, they have to format it because here is a lot of items in there, but sometimes, as you have seen in the multiple linear regression, we use the matrix approach in order to find the solutions in a very compact format. Okay, matrix solutions. Similarly, in this one, this sum of squares of the error in non-parametric regression format, we can write it. We can write it as a QG beta x equal to f of x minus tpx. I'm going to explain these things. Let me write it first. This is the way that things could be written in this format. Oh my goodness, it is gone completely. So let me write it again in this format. We had these things that I just showed you. F of xj minus beta k x p q goes 0 to p and xj minus x to the power q, and I took the square and then multiply it by the xj minus x. Let me explain this thing. In the parametric regressions, this is equal to y, this is equal to beta 0 minus beta 1 xi. And then we take the sum and then we take the square. This is what? Exactly same thing. This is what like parametric regressions. What we did in addition to that, we multiplied by a kernel. So kernel is a weighting function. Take a look at that. I have these things which is similar to the simple linear regression, error sum of square. I am just multiplying it by the kernel. Why I am multiplying this? Kernel is a weighting function. From the kernel, we will get our bandwidth, smoothing parameter we will get. Okay. So now in this case, this is exactly equal to k h x j minus x equal to k x j x over h divided by h. This is just the kernel. Okay, this kernel could be one of the 4 kernel that I'm mentioned in there. There could be many other kernel, but Ipanichnikov kernel is considered the base because it has some good properties, and that is why it is called the optimum kernel as well. Okay, and h is the bandwidth, as I mentioned earlier, same thing. Now, if I write like this way, fx could be written like this, fx1 up until fx capital J, and then if I write here beta x in this format, beta 0x, and then beta tx t, and then g x over h equal to diagonal k h x j and x with jth column zero kh x minus and tp x be the matrix with its jth row given by so if these notation are assumed, then what will happen? This one is reduced in a matrix notation to that format, q g b beta x would be fx okay. So the equations that I have written in here, you remember, in the simple and multiple linear regressions, we have these things, yi minus beta 0 minus beta 1 xi square, okay. And then in the matrix notation, what I had yi minus x beta and yi minus x beta. Simple and multiple regression. This is multiple regression M R. This is simple regression SR. This is simple regression. This is multiple regression. Similarly, in this case, this part, it reduced to that part under this structure. Okay. So now from there, the pth order local polynomial estimator, pth order the local polynomial estimator after finding the derivatives, pth order local polynomial estimator is now q takes value 0, 1, 2 up to p. So that is why I put here q, but q takes value 0, 1 to up to p. That could be written like this. W q p plus 1 x j x h f of x j. W q comma p plus 1 x j x h could be written as q plus 1 p plus 1 epx t g x comma h and then t px inverse times t jp transpose x jg x comma h. That is the derivation, and this part is called the equivalent kernel, where this is the equivalent kernel and rest of the thing as I explained before. Okay, so let me conclude this local polynomial before going to the spline one by using this. So what happened? We do not know the functional form of the fx. What the mathematician did and statistician did in 1977, they apply Taylor series of that function, expanded it, and then take the differentiation from take the subtractions of the right side from the left side, and then they took the square and then summing it and then multiplying it by the kernel, and then they said that this is the local polynomial. Why? They have a polynomial expansion. Why? They have multiplied it by the kernel in order to get the smoothing estimator. Okay. So next few minutes, 10 to 15 minutes, I'm going to discuss about spline. Spline was first discovered in 1924 by the mathematician and engineers. You know, sheep has a like this type of format, right? Spline format. Mathematics is come like that way. It was existing in there, but they borrowed this idea and applied it in the statistics in 1996, something like that, first time. And after that, there is a lot of applications. Okay. So your purpose for this homework, first try to run my code that I gave to you. I already ran it, right? I already ran this code. If I run it again, this is the code, and I got this type of figure. This type of figure I got. If you run this, then homework is just 1 hour, because you just need to change the in this place. This is the card data, you will put U data. And from the card data, you will put the X, and this is your Y. Okay. Rest of the thing, if you change accordingly, then it is your homework. Homework is done. But I ask you to do the homework by using. Understand? Try to do this by using Python. Spline regression. All the regressions that I said previously, those are known as the kernel smoothing regressions, local polynomial smoothing regression, and spline smoothing regressions. Now I am going to discuss. Why smoothing? Because regression means you got the entire curve in situation there. From there you can pick any estimated value between that line. Okay.
And do we use that local polynomial regression?
Okay. Good question. Kernel regression cannot. He asked actually very good questions. Thank you for asking. Why should I forget these things? So suppose boundary is this, another boundary is this, right? This is the whole boundary. And your other data is like this way. And you want to construct like curve like this way, right? Kernel regression cannot give better result in the boundary of the support. Okay? Because in the boundary means there is a, in terms of income, if I want to say that there are very few very poor people, there are very few very rich people, right? Do you agree with that? So in that case, boundary has a limited data points, right? In such a cases, if you see that in your boundary limited data point, use the local polynomial or spline. And other case, usually local kernel is better. Understand, right?
Whenever we don't have the idea of distribution.
What?
Whenever we don't have any idea on which distribution.
No. When you have a data point, right? And when you do the scatter plot, you see your lower point and upper point. So that means starting point and ending point. So these are the starting point, right? These are the starting point. And this is the ending point. In this case, if you see just one or two data dots, so for example, here, the figure gone. Are you seeing? Here is 1, 2, 3, right? But here is log, right? Here is log. So if you see that, like the ending, beginning and ending as only few observations, in such a cases, go for the local polynomial or spline. Understand? But if you have uniformly distributed observations, you can choose the kernel.
What is the difference between those both, local polynomial and spline?
These are the different methods of,
Same thing.
they are doing the same estimating. So same way you estimate non-parametric regression curve or smoothing curve, but different approaches used. But if you ask me question when I can use what, then my question is, if you're at the boundary, there are limited observations, okay, then use local polynomial and spline. Okay, local polynomial gives better estimate at the boundary. For example, say it's come like this way, right? So in this data point is within the 95% bootstrap confidence interval, but that one is outside. That one is outside. Now see, when this is estimating that thing, this estimate is not very good in here. But in this case, if you see, this could be better estimate for that one at least. Okay, there is a little difference between this and that. Kernel regressions cannot perform well in the boundary estimation, in the estimations in the boundary of the support. Kernel regressions cannot perform well in the estimations of the boundary of the support. Clear, right? Okay. Let me finish in next 10 minutes. What is spline 1? Spline 1, again, I want to write, purpose is to estimate this. Mx is my unknown function, which we want to estimate like this. F of x given x equal to x. See, kernel regression, we come into in estimation format by taking the expectations and then by using joint probability as well as conditional probability by plugging all of those things, and then we plug the kernel density estimations technique, then we got the final formula. But the local polynomial, the unknown function fx are expanded by Taylor expansion series, and then we subtracted the right hand side from the left hand side, and then taking the square and summation, and then finally multiplying by the kernels, and then we express those things in the format of a matrix notation we got. But here is little different. They are proposing it by mimicking some idea of the ridge regression. Ridge regression is what? Original regression exists in there and they add a penalty term, right? If you remember those ridge regression. So in natural way, to do a good approximation, approximations of this, okay, a good approximation to the true regression function is to minimize the spline objective function. Spline objective function M and H we are taking in there. J goes 1 to J, f of xj minus m of xj plus h okay. Take a look at the board. In the ridge regressions, you use this penalty, right? You remember? In the lasso, you use this penalty, right? Right? So this sum and that integration is the same, right? Integration you do for the continuous variable. Summation you do for the discrete variable, right? So you see why there is integration in there, right? And in the ridge regressions, there was a penalty parameter like the lambda, right? We have here h, okay? And then they have sum of beta z square, but we have two differentiation of square. This square come with this. These summations goes with that. So this is the ridge regression. Let me write the ridge regression. Y minus x beta, okay? Y minus x beta square plus lambda sum of beta z square, right? This is the ridge regression, right? This is the ridge regressions. So this will go with that one. Here it is known because x beta is in here. Here it is not known because mx, right? Non-parametric regression. I am making a comparison. If I ask you, spline regressions is symmetric to what kind of parametric regressions? You have to answer the questions. It is symmetric to the ridge regression, right? Okay. Here is in a state of beta Z, in parametric ridge regressions, I put here the functions which I want to estimate, but I make sure this function at least 2 times differentiable. Why 2 times differentiable? So see, x square, if you do the first derivative, then it is equal to 2x. If you do the second derivative, then it is equal to 2, right? So that means this is a continuous function, right? If it is a double differentiable, that means original function must have some kind of curve. If this is a just single time differentiable, then this is a straight line. Twice x plus 5 is a equation of a straight line, like twice x plus 5. Okay, if you differentiate this, it's just the 2, right? That is why in order to confirm that our spline or our smooth curve is 2 differentiable, I'm confirming it in here in order to make sure that the functional data or the curve that I'm looking for is a continuous and 2 times differentiable, so that when you estimate these things, it will have a property. So from there, we can write it in this format now. First one is this format. So this is called this mx. Let mx could be written like this way. This mx could be written as sum of n j theta j and j theta j and x j theta j. These things could be written as like this: square plus h j the jx theta j square dx. So let me write it in here. Why I plug these things in there? Let me write it here. Let mx j has been written in this format. J goes 1 to this and j x theta j, where n j r and j dimensional state of basis function for representing this family of natural splines. Okay, so now this is the basis j-dimensional set of basis function. This could be written in this format when the spline regression is used. In order to express these things as the j-dimensional basis function, we can write like this. In the matrix notation, we can write here when n and this belongs to by n and omega belongs to real number by nij equal to nj and xi, and it could be written like this: nix nj x dx for I comma j goes to 1 to up to j. So now the problem becomes with this matrix notations, these problems become like this. Theta comma h, it becomes f and theta transpose f and theta plus h omega theta. And the solutions for this is just the differentiation, and they got these solutions. With fitted spline, smoothing spline, sum of nj x. This is the final estimating formula for the spline smoothing estimator of our regressions. Okay, let me tell you, I covered 3 non-parametric regression in one because this is the applied statistics master degree program. You do not need to like understand maybe all of this theory, but the theory that I have covered today, it is at least a 3 lectures materials that I covered. Okay, so all the history, all of these things systematically discussed, at least 3 lectures of 2 hour 30 minutes lectures is needed. But as it is a master degree in applied statistics and decision science, for your case, most of you will get, you need to learn how to apply these non-parametric regressions in solving real life problem. Understand? So in order to do these things, as you have seen this data, if you take a look at the dimension of the cards data, I have considered 50 to 2, right? So now the question is, if you have a lot of big data, like 3000 data points, and X is something and Y is something, then your graph could be look like this. You understand? So this is a proper method when your data size could be like 100, something like this. And from there you can get a different names. Because of those 100 data points, you cannot fit any parametric regression model. If you want to see one covariate, one independent variable effect on the dependent variable, then you can use these 3 non-parametric methods. Again, if you read the theory of all of these things, there are a lot of things to discuss. How this come into and why I putting these things. In 2 hours and 30 minutes, I try to cover as much as possible so that you have a basic ideas. Okay? So from next class, I'm going to start covering time series model, and I'm going to assign you the final project. Okay? So that many of you did not do well in the conceptual part in the midterm exam, so that your grade could be bumped up. Okay? So it is 8:23. See you in next week. Have a good rest of the day. Bye.